So in the last video we were trying to get some motivation behind the idea of an exact equation. So in this video we're just going to um, forge ahead, and let's just talk about what an exact equation is. So I'm going to go ahead and scroll up to where we have some blank space here. Definition. The DE of the form m of xy plus n of xy dy over dx equals 0 is said to be exact. Oh, jeez. See if I can spell. Exact if m sub y is equal to n sub x. Good. Now, if you remember our motivation, I said I wasn't gonna do this, but I'm gonna do it anyway. We're actually comparing our exact equation with the total derivative, meaning we want m of x to be equal to f sub x for some f. We want n to be equal to f sub y. Okay, and so in order to check that, we had to use Claro's theorem to see. It's the same check that we used for the gradient vector field, right? The first function we differentiated with respect to y, second one with respect to x, and if that is true, then we were able to go backwards and construct the function whose gradient gives you p and q back in the example. Okay, so let's scroll ahead now. And so, whoops, how to solve this thing then? So if exact, let me get the better color. Don't like to draw with red. Okay, so if the equation is exact, the solution is given by f of xy equals c, where f sub x equals m and f sub y is equal to n. Good. And that is section 2.6. That is the exact equation. Good. So let's try one, just for fun. Example. How about dy over dx is equal to minus 2x plus y divided by x plus 2y. Now the question is this an exact equation or not? Now the problem is that this is not of the right form, right? So first what I'll do is I'll multiply both sides by x plus 2y, and then I'll bring the 2x plus y over. So if I do that, I would have x plus 2y dy over dx equals 0, and then bring the 2x plus y over. Okay, and so I'm thinking of this as my m, this is my n, right? And so I want to see if m sub y is equal to n sub x. And so we're really checking for the second derivatives. In this case, is it true? M sub y is equal to 1, it looks like. N sub x is also equal to 1. And so our system is exact. So now, how do we solve for little f? Well, we want f so that f sub x is equal to m and f sub y is equal to n. So therefore, taking this part of the equation, we anti-differentiate that with respect to x. And so we get 2x plus y dx. Now we're anti-differentiating with respect to x, right? So that's going to be x squared plus xy plus some unknown function of y, right? And similarly, we have f sub y equals n, right? So you could anti-differentiate that with respect to y, and we have x plus 2y dy. And so that's going to be xy plus y squared plus an unknown function of x. Is this looking familiar for those of you that watched the first video? Okay, so now we look at this. These should represent the same function. These represent the same function. Therefore, our f of y, or f of xy, must have all the pieces together. So we have x squared here. So it looks like, oops, looks like our x squared is our h of x. And by the same token, our g of y, it looks like is going to be y squared. So putting all the pieces together then, we have our function of x plus our xy, the common term, plus the function of y. Good. Am I finished? No, I'm not. Did you say you were? Because what is this? What is this thing looking at us here? Well, if you just write that, this is actually a surface in 3D, right? This is not a curve in 2D. So to get the solution, you have to set the function equal to a constant, x squared plus xy plus y squared equal to c. Good. And so this is now our solution. And you might recognize this. This is a rotated circle or ellipse, if you will, more generally. Okay. And so just for fun, let's take this differential equation and take a look at it with our plotter. So here's the equation plotter that we have. So let's see. Here's our, I don't know if I can write on this. No, I can't. So we have our direction field here, and you'll see the nice solutions there, right? By the way, you'll notice that the circle is not closed, and that's because, remember what we were saying about implicit versus explicit solutions? Now that you've kind of seen the picture, let's go back to the algebra so we can see that more. Yeah, this is implicitly defining implicit solutions, right? Because circles and ellipses do not define y as a function of x. Good. All right. What do you think? Are you ready for some exact equations? By the way, I should also say another thing about an exact equation. Exact equations, do we have to use this technique to solve? So again, when you have an exact equation, you have m plus n dy over dx equals 0 with m sub y equal to n sub x, where the solution is f, and we want, or I guess you could say where we want f equal, or f sub y, f sub x equal to m, and f sub y equal to n. Good. Okay. Do we have to use this technique to solve? Well, yes, we do. But I wonder if we could take a look at a different, I got a little mixed up on that one. How about true or false? All separable equations are exact. I wonder if that's true. dy over dx equals, so if it's an exact, if it's separable, you can write it as f of y times g of x. And notice that in that case you can write this as 1 over f of y prime. Let's bring the g of x over to the other side, minus g of x equals 0. So this would be our m, this would be our n. What is m sub y? It's 0. What is n sub x? It's 0. Yes, it is exact. Yes, it is exact. So all separable equations are exact. Now the question is would you want to use this technique to solve a separable equation? Well, as you can see here, right, as soon as you integrate your m with respect to x, right, you're going to be taking the g of x dx, which you need to anyway, and similarly n dy would be your 1 over f of y, integral dy, which you would need to take anyway. So you're actually computing the same antiderivatives either way. Good. Alright, so the next video is just going to be examples. See you then.